In the 9th century, during China's Tang dynasty, a group of Taoist alchemists mixed sulfur, charcoal, and saltpeter inside their furnaces. Their goal was not warfare, but longevity. They pursued the idea of the golden elixir, a pill believed to extend life beyond the biological limits of roughly 70–80 years, adding decades to the average lifespan of the ancient world. Instead of prolonging life, the mixture produced heat and light in an instant. From that moment, history veered in a direction no one had intended. The contradiction lies here. The same set of chemical elements, with only a change in proportions and environment, can shift from medicine to explosive. Chemistry does not care about human intention. It follows bond energies and the laws of thermodynamics. When the alchemists recorded scenes of smoke and flames rising, burning beards and hair, they were describing a powerful redox reaction, not magic. To understand why the search for immortality led to gunpowder, we must return to the philosophical and technical foundations of alchemy at the time. There were beliefs, experiments, and carefully documented mistakes. Taoist alchemy was more than faith. It was a form of proto-chemistry. Practitioners observed phenomena, recorded reactions, and repeated procedures. Saltpeter, or potassium nitrate, was often collected from soil rich in animal waste and organic ash. This compound contains nitrate ions, nutriments, a strong oxidizing source. Sulfur was mined from natural deposits, while charcoal was nearly pure carbon, created through the pyrolysis of wood at around 400–600 degrees Celsius, hot enough to remove most water and volatile compounds. When the three ingredients were finely ground and mixed, the contact surface between molecules increased. Doubling surface area can dramatically accelerate reaction speed because it creates more collision points between fuel and oxidizer. To alchemists, this was a technical step to activate medicinal properties. To modern chemistry, it is the ideal condition for a rapid exothermic reaction. Tang-era texts warned against mixing sulfur and saltpeter with honey or oil because the mixture would ignite violently. Honey provided sugar, an easily oxidized form of carbon. When nitrate decomposes at high temperatures, it releases internal oxygen that does not rely on the surrounding air. The reaction occurs within the material itself, explaining why the mixture can burn even in relatively enclosed environments. The quest for a liquid gold elixir inadvertently created a self-oxidizing chemical system. One more step, and this accidental invention left the alchemy chamber and entered society. At the core of black powder lies the oxidation reaction between carbon and nitrate. When ignited, potassium nitrate decomposes, supplying oxygen to carbon and sulfur. Carbon oxidizes into CO and CO2. Sulfur forms SO2. Each mole of gas produced causes a sudden increase in volume. Under standard conditions, 1 mole of gas occupies about 22.4 liters. If dozens of moles form in a confined space, pressure rises extremely fast. That pressure becomes the basis of propulsion. Reaction temperatures can exceed 2000 degrees Celsius, enough to soften metal if enclosed. However, black powder is not a high explosive like TNT. It burns rapidly in a process called deflagration, meaning the reaction front travels below the speed of sound. This explains why it suits fireworks and early weapons, but does not produce the supersonic shockwave associated with modern explosives. Sulfur plays the role of lowering the ignition temperature. Pure carbon requires high heat to burn. With sulfur added, the mixture ignites more easily, meaning even a small spark can trigger it. This factor made the alchemists' experiments unexpectedly difficult to control. Once the mechanism became clear, the story moved beyond the laboratory. Any material capable of rapidly generating gas tends to find its way into applications that require thrust. The distance from religious ritual to battlefield was shorter than anyone imagined. Initially, gunpowder was used in fireworks during festivals. Early fireworks were bamboo tubes packed with powder. When ignited, they produced loud bangs and flashes of light. In folk belief, The sound drove away evil spirits. From a physical standpoint, the bamboo created a confined space that allowed expanding gases to burst the casing. That simple structure became the ancestor of barrel-based weapons. By the 10th and 11th centuries, Chinese military records described fire arrows, tubes filled with gunpowder attached to arrows. When ignited, gas expelled backward, generating thrust according to Newton's third law. Every action has an equal and opposite reaction. If a mass of gas shoots backward at several hundred meters per second, the arrow moves forward with corresponding momentum. This is the basic principle of jet propulsion. The Silk Road transported not only goods but also technology. Gunpowder spread to the Middle East and later to Europe within a few centuries. In each region, ratios and manufacturing methods were adjusted. A small change in the familiar proportion, roughly 75% saltpeter, 15% charcoal, 10% sulfur, determined the rate of gas generation. This ratio balances fuel and oxidizer, preventing excess material from reducing efficiency. An experiment meant to discover immortality marked the beginning of the artillery age. The paradox reminds us that technological progress often emerges at the intersection of curiosity and error. If one day you encounter an ancient formula containing 3 familiar ingredients, remember that behind them lies thousands of years of experimentation, documentation, and unintended consequences. The story of gunpowder does not end here. From those black grains, advances in granulation, compression, and burn rate control paved the way for modern industrial chemistry. Exploring how a crude mixture was transformed into a stable system capable of traveling across continents is another remarkable chapter waiting to be told.